Hi, my name is Bianca Lopez Parnetti, and this is my presentation on Lab 2 Projectile Motion. So the purpose of this lab was to record the motion of a projectile and then create a computational code that modeled the predicted movement off of the recorded projectile on the same conditions, and then finally compare the kinematics or the forces on both the observed system and the predicted system. So the two main physics principles used in this lab were kinematics and forces. Under kinematics, we used Newton's second law or the momentum principle and also displacement. And under forces, we had the two forces acting on the system, which we changed, gravity and drag. And the relevant equations here were Newton's second law, net force is equal to mass times acceleration, which we have gravity and also drag, as said before. And then we also measured change in displacement using velocity and time, and then also acceleration. So as a preview of the results, we can see that both the observed and the computational system graphed out the displacement with drag and also without drag. And we can see that the computational system did not accurately model the displacement but with drag, but it did accurately show it without drag. Both of them had a linear displacement without the drag, but only the observed model had a polynomial displacement with drag. So the system for this lab was just a ball of paper, as seen in the picture, and then the surroundings was everything else that was interacting or in contact with the paper ball. So for example, the hand that threw the ball, the table if it came in contact, and then also the atmosphere with drag. So the initial conditions for the experiment were the same in both models. They were taken from the observed experiment and then plugged into the computational code. So you have the initial position, the initial velocity, the mass of the system, the initial time, and then the time step. So to create the observed model, we recorded a video of the ball being thrown in the air as a projectile, and then we uploaded it onto the tracker platform. We tracked the paper ball as a point mass, so one data point per frame, and then we uploaded it onto a data table of time and position, and then we used it on Excel. So then on the left, you can see the different coordinates it pushed out. So you have the time value, and the X shows the displacement without drag, and then the Y shows the displacement with drag. And next I created the computational model. The first part shows the code to visualize and graph the object's movement, then all the initial conditions for the system, and there were two systems created, similar to the observed one. There was one with drag and one without drag. And then finally the coded calculations to solve for the changes in position based off the initial conditions. And here is just the visualization of the graphs that was given in GlowScript from the code. So the overall results showed two very different models in terms of displacement. As mentioned before, the observed model had perfect linear displacement without drag, but then with drag it made almost basically a perfect parabola. But then in the computational system, it should have done the same thing, but it didn't. Both of them were still very linear, so it didn't really graph out the results properly. So just to make it a bit clearer with similarities and differences, the similarities were that displacement without drag was linear in both models, and then with drag, both of them did have some downward variance towards a polynomial shape. But then the difference was that the displacement with drag in the observed system was actually a polynomial, while the linear one was just linear with some variance in the computational system. And also the observed system displaced farther, which was almost 2 times the distance of the computational. And then some possible sources of error. There's always some kind of human error incorrectly mapping each data point on tracker, and then also because tracker was used on a MacBook, there's a lot of glitching and distortion in the video. And then the assumption of perfect conditions. We didn't actually calculate the drag, we just used a set number, so it's not perfect. And then for the additional questions, the first one was a what if, and it asked if any of the models predicted a terminal velocity, and I said the terminal velocity would occur when the velocity was at a constant value, meaning the slope would be 0, and this occurred in all the linear systems and in the observed system at the peak of the polynomial, so there was a terminal velocity seen in the graphs. And for the what does it mean question, it asked which kind of system would take longer, either the one that we actually performed or one that would be thrown straight up. And I said the one that would be launched straight up at 90 degrees because it would the increased launch angle would max out the time spent in the air. And those are my calculations, so it showed that there would be additional time. And that's it. Thank you so much for listening.